Hello, my name is Muhammad Amin Ghasamzadeh, and my peer in this project is Mr. David. The topic of this project is the connection of a large renewable station with pumped hydro storage to the Australian National Grid. The first hydro pumped station built from turbines and pumped in Europe in 1890s. With the increasing cost of the greenhouse gases, the demand of the renewable energy and the pumped power planet is increasing too. As you can see in this slide, if the demand of the electricity from the grid is less than the PV system, turbine pumped water from the lower storage to the upper storage. And if the demand is more than the PV system, the water is allowed to flow back to the ground to provide the electricity. The advantage of using this system are the hydropower availability, the peak load smoothing. It helps to control the voltage and frequency. We don't need the fuels for this system. And the disadvantage for this system is affect on the population of the fish and the quality of the water, and also it can be affected by drought, and the cost of this system is high. There are some other forms of storage that we listed here, such as thermal energy storage, compressed air energy storage, energy storage using the follow batteries, chemical storage, and the energy storage in supercapacitor. As you can see, the result in this figure from the PSSE, the bus voltage meets the standard rate. But as it is illustrated in the next slide, the reactive capability of the generator at bus 203 doesn't cover the standard rate. For the solve this problem, we have two ways. First, we can decrease the voltage from 1.05 to 0.95, or we can put the capacitor that have at least 400 megawatt reactive power. In this table, we can see the harm rate which is calculated for this project. And as you can see in this table, our PV system cannot pass stage 2. It's not okay. So our PV inverters need LCL filters or the active filters for its output power. The short-term flicker emission limit is 0.35, so EPST is 0.205, which is calculated from this equation. If according to this figure, if we assume the rectangular voltage change per minute is equal 1, the delta U divided by U is equal to 2.8% for PST1. Our PST is 0.205, so delta U divided by U is equal 0.5% for rectangular voltage change per minute 1, and it is 1.43% for the rectangular voltage changes per minute 0.1. As you can see in this table, which is located in the page 21st of the report, we disconnect one circuit of the our feeder to the farm, solar farm. Then we did the load flow again to check the voltage following disconnection fault. All the voltage meets the standard rate, which is 0.9 to 1.1 per unit. In this graph, you can see the rate of change of frequency when the hydro and PV in service. In the next graph, you can see the rate of the change of frequency when the hydro and the PV out of service. You can see this one is a little bit greater than the last one, the previous one. And also they will return to a steady state. For the next slide, my friend David continue this presentation. Thank you.
So to continue the presentation, I'm going to talk about